Welcome once again to this online session. We are discussing diode circuits, and today we will discuss the topic of clampers. Like flippers that we had discussed before, clampers are also one of the important diode circuits which finds application in varieties of systems. Let me start with the presentation and explain what clampers are. If we try to go through the definition of what clamper circuits are, then clampers are those electronic circuits that changes the DC level or the average value of a signal without changing the shape of the signal. What do I mean by changing DC level or the average value? If I change the DC level or the average value of a signal, the whole signal would move up or down. It means that the level of the signal would be shifted. Let us try to understand this by taking a very simple example. We all are familiar with this waveform. Yes, this is a sinusoidal waveform with a peak at plus 5 and peak on the negative side at minus 5. If we try to calculate the average value or the DC value of a sinusoidal signal, then we know that the DC value basically can be calculated by integrating the waveform over one period. That is, VDC is equal to 1 by T, where capital T is the time period, integration 0 to T, V0 dt. So if I integrate this waveform over one period and I divide it by the period, what I would get would be the average value or the DC value. If we try to do this for this signal, we can understand that the average value of this would come out to be 0. We can understand this in a very simple way as this. We all know integration is basically addition. So, in the positive half cycle, the values that I add, to this I would add also the values which are in the negative half cycle. These are having positive values, these are having negative values. So, when I add this two over one period, the net value would come out to be equal to 0. So the average value or the DC value of a sinusoidal signal is 0. Now to this signal, let us try to add another signal which is a pure DC signal. This is a DC signal of plus 5 volts, right? If I add this two signals, what would be my output signal? To add these two signals, I would have to add point to point. That is, let us try to see what is the value of the signal at time t equal to 0 here. It is 0. What is the value here? 5. So 0 plus 5 would give me 5. What is the value of the signal at this particular point of time? It is plus 5. Now if I take the value of this signal at the same time, what is the value here? This is 5. So 5 plus 5 would be 10. Similarly, this would be 0 plus 5, so it would be 5. Similarly, minus 5 plus 5 would be 0. So if I try to plot this signal, I would get some signal like this. At time t equal to 0, 0 plus 5 would give me 5. 5 plus 5 would give me 10. Minus 5 plus 5 would give me 0. So we can understand that the whole sinusoidal signal, the shape is remaining same, but the signal has shifted up by 5 volts. This is actually what we understand by the meaning of clampers. Let us come back to the definition of clampers. Clampers are electronic circuits that basically changes the DC level or the average value of a signal without changing the shape of the signal. So the shape of the signal is remaining same, it is sinusoidal signal, but here the average or the DC value was 0, here the average or the DC value is 5 volts. This is what basically clampers do. Because clampers shifts the level of the signal, they are also called as level shifters, right? So, to summarize, clampers are electronic circuits that changes the DC level of a signal without changing its shape. It moves the whole signal up or down. They are also known as level shifters. Now, the clamper circuits that we would study would primarily consist of diode, capacitor, and a resistor, right? And depending upon what type of clamping, what type of level shifting does a clamper circuit do, we can classify clamper circuits as follows. We may have positive clampers, that is, if a positive DC voltages are added to a signal so that the signal gets shifted upward, then they are called as positive clampers. Similarly, negative clampers are those where the DC value is added so as to shift the signal downward. So I will be basically adding a negative DC voltage so as to bring the whole signal down. These are called negative clampers. We may also have clamper circuits where I would be using additional voltage source. Such type of clamper circuits are called biased clampers. So such circuits would have voltage source along with a resistor, capacitor, and a diode. What are the popular applications there where we can find clampers? In fact, clampers are found at a number of places. They are basically called DC restoration circuits. You would study, when you would study transistor based amplifiers, that because of capacitive coupling, the DC from the signal gets removed. So to restore such DC, clamper circuits are used. They were very popular circuits in CRT based television. Another example where clamper circuits can be used is converting a bipolar signal into a unipolar signal. What do I mean by this? Is suppose that you have a circuit which can take only positive voltages and not negative voltages. But actually, your signal varies in both direction, positive as well as negative. So what you can do is that you can clamp your signal at a level such that all the voltages now remain positive. So what happens is that without changing the shape of the signal, without changing the manner in which the voltages are changing, a bipolar signal gets converted into a unipolar signal. Such applications you can find when you are using A to D converter. Another popular application of clampers, which we would discuss later in this session, is voltage multipliers. They are basically used as voltage multipliers. So in short, clampers find wide varieties of applications in different electronic systems. Now, let us try to take examples of clampers one by one and let us try to understand how the shifting of DC level is achieved. Let us start with understanding of charging and discharging of capacitor before actually moving on to the circuits of clampers. Because clampers uses capacitors, it would be very helpful for us if we understand how capacitors behave. We know that capacitors are basically charge storing devices. It basically stores energy in form of charge, and more the charge is stored inside a capacitor, more would be the voltage across the capacitor. Let us try to take a simple circuit here. Kindly follow my cursor. Let us try to take a simple circuit here. I do have a switch, and switch can be positioned at A or switch can be positioned at B. Let us try to assume that initially the capacitor is uncharged. It means that it is not having any charge, and the switch is at position A. This would basically give me a circuit like this. It would have a voltage source Vn, which is connected to an RC network. As the loop is closed, the current would start flowing through the circuit. And as the current flows, the charge across the capacitor starts getting stored and the voltage starts getting developed. We are aware about the basic relations of voltage, charge and capacitance. Q is equal to CV, and the voltage across the capacitor Vc can be given as 1 by C integration of 0 to T it dt. So as the current flows through the circuit, the voltage across the capacitor starts increasing. What would be the nature in which this voltage would increase? This is again something what you might have studied in the basic course on electrical engineering, charging and discharging of a capacitor in an RC network. So if we try to see, then the voltage across the capacitor would exponentially increase. It would increase exponentially. And to what value would the voltage increase? The voltage would increase to the value equal to the supplied voltage, Vn. So slowly, the voltage across the capacitor would reach to Vn. If you try to understand, then in this circuit, the net voltage which are acting is Vin minus Vc. So as Vc increases, Vin minus Vc would decrease. And what would be the value of current? The value of current would be Vin minus Vc divided by the total resistance R in the loop. So as Vc increases, the net voltage in the circuit decreases and hence the current would decrease. When the voltage across the capacitor would become equal to Vn, we would say that the current in the circuit would become equal to 0. So if we try to see how the current changes, then the current in the loop basically decreases exponentially. Now the question arises that how fast or how slow would the capacitor charge? It means that what would be the speed at which the capacitor would charge? Then we are aware that this primarily depends upon the time constant of the circuit. What is a time constant? Time constant is basically the product of R and C. So for a given value of capacitor, if I select a particular value of capacitor C, then if R is large, then RC would be large, that is your time constant would be large, and hence my charging would be slow. If I try to come to the graph again, then you can understand that at around 4 times time constant, this is your time axis. So at about around 4 times time constant, it almost reaches to 98%. At 5 times time constant, it almost reaches 99.9%. Right? So if I say my time constant is 1 second, then you can assume that in 5 seconds, this becomes equal to Vm. Now, if R is large, this time constant would be large. So 5 times time constant would be large, and hence we would say that the charging is slow. But if the R is small, then time constant is small, and hence we would be able to achieve fast charging. So instead of 1 second, if I say that my time constant is zero point 0.5 seconds, then this can be achieved in 2.5 seconds, right? Taking the extreme case, suppose that I say that my resistance is 0, then time constant is 0. What does this mean? What does this mean? This means that the charging is immediate. The charging is immediate. Capacitor immediately would charge to the given voltage. And this is what is going to happen in many of the circuits of clampers that we will see. Right? So this is the charging of the capacitor. Now, considering that the capacitor is charged to Vc, let us try to see how the discharging of capacitor takes place. So now suppose that I shift this switch from position A to position B. So the circuit that I would get would primarily be something like this. So here the capacitor now is charged to Vn. So the capacitor would work as a voltage source and it would start discharging through this resistor. It means that whatever is the charge which is stored inside the capacitor would start to flow and the capacitor would discharge. As the capacitor would discharge, the voltage across the capacitor would decrease. So the voltage from Vin decreases exponentially, and till the time capacitor becomes totally uncharged, the current would flow. Initially, if we see this loop, the voltage acting in this loop is Vc. So as the voltage is decreasing exponentially, the current in the loop, which would be equal to Vc by R, would also decrease exponentially. So this would be how the voltage across the capacitor Vc and the current flowing through the loop would basically change. Again, the question is that how fast would this discharge? Then this again depends upon the time constant, same time constant Rc. If R is large, T is large, so my discharging would be slow. And if R is small, T is small, my discharging would be fast. If I again take an extreme case where I say that my R is very large tending to infinity, it means that T is very large. What does this mean? This means that discharging time is very large, so there is very slow discharging, almost zero discharging. It means that capacitor would retain the voltage Vc. The charging is very, very slow. It can be approximated to be no discharging, so the capacitor would retain the charge. When would this happen? This would happen when this resistor is of very, very large value, right? Now, let us try to bring this discussion of charging and discharging of capacitor close to the discussion of clamper circuit. Let me try to give you an example as shown here. What do I have? Consider that we have a capacitor which is initially uncharged, and I have a diode instead of a resistor, and I have a sinusoidal source. I have a sinusoidal source instead of a DC source, right? So what would happen? We can easily estimate that so far as the positive half cycle of the input voltage is concerned, the diode would get forward bias because I would have a positive voltage is here, negative voltage is here, diode would get forward bias. Diode, if I consider it to be ideal, then the resistance of the diode would be zero. The diode would allow the current to pass and the capacitor would charge. Now, considering diode to be ideal, if its resistance is zero, the charging time constant of the capacitor would be zero. Why? Because on what does time constant depend? Time constant is R into C. What is the resistance in this circuit? The resistance can only be the resistance of this diode, and we have considered it to be ideal, so the resistance is zero. So time constant is zero. So if the time constant is zero, the charging would be immediate. So as the input grows, the voltage across Vc would follow, right? When input voltage would become equal to Vm, it means that the peak voltage, when the input would reach to the peak voltage, Vc would also reach to the peak voltage. What happens after this? So when the input voltage in the positive half cycle reaches to the peak voltage, Vc is also equal to Vm. Now the input voltage starts decreasing from Vm. So the potential here on the P terminal of the diode is less than Vm, but on the N side you have Vm. So diode would basically become reverse bias. I again repeat this. This is something which one has to understand, that when input voltage reaches to Vm, the voltage across capacitor would be equal to Vm because there is immediate charging. Now, after this, the input voltage decreases, so the voltages which are at P terminal would decrease. But what is the voltage at N terminal? The voltage at N terminal is Vc, which is equal to Vm. So the voltage at N terminal is Vm, whereas at P terminal it is less than Vm. So diode would become reverse bias. Diode becomes reverse bias, it acts as an open circuit. So capacitor actually does not have any chance to discharge, because for discharging it needs to have a closed loop. But the diode is now reverse bias, so it does not have, it does not provide us the closed loop, and hence the capacitor cannot discharge. So the capacitor would maintain its voltage equal to Vm. So if we try to see, this would be the relation of, or this would be the waveform of VC. Initially, it would charge up to Vm along with input voltage, and then it would maintain Vm to be equal to constant. Because after this, the diode would never come into a forward bias state. This understanding would be quite useful so far as understanding of clampers are concerned. Now let us try to study different examples of clampers. Let us start with the example of a negative clamper. I could have taken the example of positive clamper first, but this would be something which would be more easier to understand compared to a positive clamper, right? So let us try to consider a simple circuit of a negative clamper. I'm not using any DC source here, so this is an unbiased clamper. What is the circuit configuration? I do have a capacitor here. I do have a diode which is in shunt with my RL, and my output is taken across the diode. Right? What is my input voltage? My input voltage is again sinusoidal signal with a peak at Vm and negative peak at minus Vm. Right? Let us try to understand. Let us try to understand how would this circuit behave. Let us first try to estimate that what would be the output voltage V0 when the diode is on, and when the diode is off, right? So if the diode is in on condition, then ideally the diode works as a closed switch. So this branch is short circuit. The voltage across a short circuit branch is zero. And let us remind ourselves that the voltage which is voltage across the branches that are in parallel would always remain same. So if the voltage in this branch is zero, the output voltage would also be zero. Similarly, so when the diode is on, the output voltage is zero. Similarly, when the diode is off, then what would be the voltage? When the diode is off, then this acts as an open circuit. Now, if this acts as an open circuit, if this acts as an open circuit, what would be your loop? Your loop would be V in, capacitor, and RL. So, what would be the voltage across RL? The voltage across RL would be equal to V in minus VC. We have assumed the polarity of capacitor here to be positive, here to be negative. So, this is V in minus VC, assuming that V in would be positive here and negative here. V in minus VC would be the voltage across RL. Right? So when the diode is in on condition, it acts as a closed switch. So this is short circuit, so output voltage would be zero. When the diode is off, it is reverse bias. It acts as an open switch. So consider that this part is not in the loop now. Now your loop is this, and we are trying to find voltage across this. So what would be the voltage across this? It would be input voltage V in minus voltage across capacitor VC. So V in minus VC. Now let us try to look at this in context with the input voltage applied. Let us try to take the positive half cycle first. Let us assume that the capacitor initially is 0, so the value of Vc is equal to 0. Now, as in the positive half cycle, this terminal is assumed to be positive, this terminal is assumed to be negative. Right? So, as the voltage increases from 0 to Vm, because this is initially 0, the diode would come into a forward bias state. Right? What is the case? The case is you have this terminal to be positive, this terminal to be negative. The voltage across the capacitor initially is 0, so the diode is in forward bias condition. Diode is in forward bias condition, and hence your output voltage would be 0, but the current would flow in this loop. The current would flow in this loop, and hence the capacitor would charge. Now, How fast would it charge? Then what is the resistance in this? What is the time constant of this loop? Then you actually don't have any resistance because diode, ideal diode acts as a closed switch with resistance to be zero. So the capacitor would charge immediately as per the input that appears. So as the input is increasing, kindly follow my cursor. As the input is increasing, the voltage across the capacitor would also increase. This is what we try to summarize here. That in the positive half cycle, till the time input voltage is less than Vm, I am talking about this initial part. This initial part, right? Till the time the input voltage is less than Vm, the diode would be forward biased and hence the output voltage would be zero. This is what it this is what is shown here. The output voltage is zero, right? The current will flow through the diode, the current will flow through the diode, and the capacitor would be charging equal to the input voltage Vi. And the charging would be immediate. Why? Because the time constant is zero. So up to what value the capacitor would charge? The capacitor would charge up to Vm. After this, what happens? After this, what happens is that the input voltage is now decreasing. Input voltage is becoming less than Vm, but voltage across the capacitor is equal to Vm. So the voltage which is available at P terminal is now minus Vm, and at N terminal you have voltages which are higher than minus Vm. So what would happen? What would happen is that the diode would immediately go in a reverse bias state. So after the input voltage crosses Vm, the diode would go in a reverse bias state. And as soon as the diode goes in a reverse bias state, what would be the output voltage? Now output voltage would be equal to Vin minus Vc. What is Vc now? The voltage across the capacitor is now equal to Vm. So the output voltage would be equal to Vin minus Vm. So what does this mean? This means that if my voltages are equal to zero at the end of the positive half cycle, what would be my output voltage? It would be 0 minus Vm. So on the output side, I would get minus Vm voltage. So just right now, just focus on the input waveform between time t equal to 0 and the line that I have drawn, that is positive half cycle. For this positive half cycle, this is the nature of the output waveform. From 0 to say 90 degrees, the output voltage would be 0 because the diode is on and capacitor is charging. From 90 to 180 degrees, my output voltage would be equal to Vin minus Vm. So this is what would be the relation. When the input voltage is 0, the output voltage would be equal to minus Vm. So this is what happens in the positive half cycle, the first positive half cycle. From time t equal to 0 to this blue line, this is the nature of the output voltage here. Now let us try to consider would there be any discharging of capacitor or not? When we say that the diode is reverse biased, then the loop is this. So in this loop, we have a resistance RL. So current would naturally pass through RL, but now if I say that the value of RL selected is very large, then the capacitor would discharge, but would discharge at a very slow rate, and hence we can approximate that the voltage across the capacitor would almost remain equal to Vm. So here the condition that we have assumed is that when the diode is reverse biased, this is the loop that I have. The current certainly flows in this loop, but the value of the current flowing is very, very small. Why? Because RL is very large, and because of that, the time constant is very large. So we can approximate that the discharging of capacitor is very slow, and hence it would maintain voltage equal to Vm. Let us move on to the negative half cycle. That is, now we are talking about this part of the circuit, this part of the input. So what would happen in a negative half cycle? In negative half cycle, this terminal would become negative, this terminal would become positive. The capacitor is charged to Vm. What would happen to this diode? We can understand N terminal connected with positive, P terminal connected with negative. Diode would remain reverse bias. Diode would remain off, and hence what would be the output voltage? Output voltage would be equal to Vi minus Vc. What is the value of Vc? Vc is equal to Vm. So the output voltage would be equal to Vi minus Vm. What does this mean? It means that when the input voltage becomes minus Vm, so when this becomes equal to minus Vm, minus Vm would give you minus 2 Vm. So I would get my negative peak now at minus 2 Vm. I would get my negative peak on the output side at minus 2 Vm. So if we try to see the negative half cycle, the part of the input waveform between these two lines, then this is the waveform that I would get, right? When input voltage is 0, 0 minus Vm, I would get it equal to Vm minus Vm. When input voltage is minus Vm, minus Vm would give you minus 2 Vm. Again, when the input voltage becomes equal to 0, 0 minus Vm would give you minus Vm. Again, we can say that there would certainly be some current which would be flowing here, but the value of the current would be very less, considering that the value of RL is very large, the time constant is very large, and hence the capacitor would discharge at a very slow rate, and we can assume that the value of the capacitor, sorry, the voltage across the capacitor remains almost constant, equal to Vn. This is something which is very critical for clamper circuits. The value of the resistor that you are supposed to take should be very large, so that the discharging of the capacitor is relatively very slow. So now if we try to understand the positive and the negative half cycles together, then we understand that once the capacitor is charged to Vm, whether it is positive half cycle or whether it is negative half cycle, diode would always remain in a reverse bias state, and hence the output voltage would continuously be V0 equal to Vi minus Vm. So now you can understand that in the output you get the input voltage shifted by a constant value minus Vm. Thus, the input voltage is pulled down by the value of minus Vm. As the waveform shifts towards the negative side, we call this to be a negative clamper. I'm sure you would have understood this basic operation of a negative clamper.